This is a training module on the ST Microelectronics LIS3LV02 3-axis digital output accelerometer. Welcome to the training module on the LIS3LV02DQ 3-axis digital output accelerometer. Here we introduce ST's 3-axis plus or minus 6G digital output low voltage linear accelerometer. Microelectromechanical systems, MEMS technology, is one of the most exciting areas in the field of analog technology. The principles of MEMS technology are based upon the mechanical properties of the silicon. Silicon is stronger than steel in about a third of the weight, and it's used to create moving structures within the device. Combined with microelectronics, signals generated by the moving structures give perception and control capabilities to create a new generation of sensors. Sensitive and compact inertial sensors based on MEMS technology allow systems designers to add new capabilities to their products that make them easier to use, more functional, and more reliable. Commercially available MEMS sensors are widely used to enable advanced motion sensing functions, including portrait landscape rotation, pedometers, menu browsing, free-fall recognition, personal navigation, or inclination detection. Typically, a MEMS accelerometer consists of interlocking fingers that are alternately moving and fixed. Acceleration is sensed by measuring the capacitance of the structure, which varies in proportions to changes in acceleration. The elements can be arranged like combs to make a linear accelerometer as used in airbags, or like the spokes of a wheel to make a rotational accelerometer. These MEMS devices are mainly used in the automotive market in airbags to detect very high G levels. They are also used in the rollover detection systems and in vehicle dynamic control systems to detect low G levels. The LIS3LVO2DL is a low-power, low-voltage linear accelerometer with an SPI I2C interface that allows implementation of an easy and intuitive user interface. This highly efficient device accurately measures acceleration in 3 axes while consuming very little power. Due to its embedded non-volatile memory, all critical device parameters are trimmed and stored during final tests to enable uniformity of production. The LIS3LV02DL has a user-selectable full scale of plus or minus 2G, plus or minus 6G, and it is capable of measuring acceleration over a bandwidth of 640 Hz for all axes. The device may be configured to generate an inertial wake-up free-fall interrupt signal when a programmable acceleration threshold is crossed, at least in one of the 3 axes. The small size and weight of this package make it an ideal choice for handheld portable applications such as cell phones and PDAs or any other application where size, weight, and package performance are required. The MEMS accelerometers allow the implementation of some important safety features in portable devices, including free-fall detection, to protect the integrity of hard disk drive data, and shock detection. In an anti-theft system, the accelerometer can be used as an inclinometer, which senses the inclination of a car or motorbike versus the ground. In car navigation, the accelerometer can assist the GPS if the signal is lost. The LIS3LV02 3-axis linear digital accelerometer includes a MEMS sensor chip that changes capacitance in response to movement or inclination. In the same package, there is a trimmed interface with an embedded 12-bit ADD converter that translates this capacitance change into a digital word which can be read by a serial interface. The complete measurement chain is comprised of a low-noise capacitive amplifier which converts into an analog voltage the capacitance unbalancing of the MEMS sensor, and by 3 delta analog to digital converters, one for each axis, that translates the produced signal into a digital bit stream. The delta converters are coupled with dedicated reconstruction filters which remove the high-frequency components of the quantization noise and provide low-rate and high-resolution digital words. The acceleration data may be accessed through an I2C SPI interface, thus making the device particularly suitable for direct interfacing with a microcontroller. The LIS3LV02 features a data radius signal, RDY, which indicates when a new set of measurement acceleration data is available, thus simplifying data synchronization in digital systems employing the device itself. A proprietary process is used to create a surface micro-machined accelerometer. To be compatible with the traditional packaging techniques, a cap is placed on the top of the sensing element to avoid blocking the moving parts during the molding phase of the plastic encapsulation. When an acceleration is applied to the sensor, the proof mass displaces from its normal position, causing an imbalance in the capacitive half bridge. This imbalance is measured using charge integration in response to a voltage pulse applied to the sense capacitor. At steady state, the nominal value of the capacitors are a few picofarads, and when an acceleration is applied, the maximum variation of the capacitive load is up to 100 femtofarads. The digital interfaces available in the LIS3LV02 device are I2C or SPI serial interface. The acceleration data may be accessed through an I2C SPI interface, thus making the device particularly suitable for direct interfacing with a microcontroller. The table shows serial interfacing signals like chip select, SCL/SPC, SDA, SDI, and SDO. The registers embedded inside the LIS3LV02 DQ may be accessed through both the I2C and SPI serial interfaces. The SPI serial interface may be software configured to operate in either a 3-wire or 4-wire interface mode. The serial interfaces are mapped onto the same pads. The LIS3LV02 I2C is a bus slave. The I2C is employed to write the data into the registers, whose content can also be read back. The relevant terminology is given in the table. There are 2 signals associated with the I2C bus, the serial clock line SCL and the serial data line SDA. The latter is a bidirectional line used for sending and receiving the data to and from the interface. Both the lines are connected to VDD through a pull-up resistor embedded inside the LIS3LV02. When the bus is free, both the lines are high. The I2C interface is compliant with fast mode 400 kHz I2C standards, as well as the normal mode. The LIS3LV02 SPI is also a bus slave. The SPI allows write and read of the registers of the device. The SPI interacts with the outside world with 4 wires: chip select, SPC, SDI, and SDO. CS is the chip select, and it is controlled by the SPI master. SPC is the serial port clock, and it is controlled by the SPI master. SDI and SDO are respectively the serial port data input and output. Those lines are driven at the falling edge of SPC and should be captured at the rising edge of SPC. Both the read register and the write register commands are completed in 16 clock pulses, or in multiples of 8 in the case of multiple byte read-write. Bit duration is the time between 2 falling edges of SPC. The device core is supplied through the VDD line, while the I/O pads are supplied through the VDD I/O line power. Power supply decoupling capacitors, 100 nanofarad ceramic, and a 10 microfarad aluminum electrolytic should be placed as near as possible to pin 13 of the device. All the voltage and ground supplies must be present at the same time to have proper behavior of the IC. It is possible to remove VDD maintaining VDD I/O without blocking the communication buses. The functionality of the device and the measured acceleration data is selectable and accessible through the I2C SPI interface. When using the I2C, chip select must be tied high, while SDO must be left floating.